Hi everyone. Addressing your feedback from today. Let's see. I'm still having a little trouble telling which order goes with which equation. And yeah, especially when we get into something like kinetics, when there's three different equations essentially that you need to be aware of for each order. Yeah, there's a lot to sort of keep track of. But there is some amount of a logical flow to it in the sense that, okay, you figure out which, this is usually how a problem will go. It's just you figure out which order the reaction is, and then depending upon that order, these are the three equations that describe its kinetics. So if I have a first order reaction, the rate of that reaction is linear with the concentration. It goes as the first power of the concentration. Its concentration follows a logarithmic function, or rather follows an exponential function. And so there are basically three types of things that you want to know. You want to know, how does the rate depend on concentration? That's given by the rate law. You'd want to know, how does the concentration depend on time? That's the integrated rate law. And then you want to know the half-life equation, which is in some sense also related to how does the concentration relate to time. So half-life, maybe I shouldn't have taught it this way, but I frequently try to teach half-lives and integrated rate laws together because half-lives are derived from integrated rate laws. A half-life tells you the time it takes for the concentration to drop by a half. So it depends on how the concentration relates to time. So they are conceptually very much closely related. They are just for a very specific case for the time it takes for the concentration to drop by 50%. What else? So working backwards, though, you can work backwards. So for instance, I gave a couple of questions today where basically I told you something about the half-life and you were supposed to work out something about the order. So if I told you there's a reaction and its half-life is constant with time, its half-life is constant. Well, in any reaction, the concentration changes with time. So the zeroth and second order reactions, their half-lives depend on concentration, meaning that those half-lives change as the reaction proceeds. So that means if I tell you a reaction has a case where its half-life is independent of time, is independent of concentration, there's only one case where that can be, which is a first-order reaction. Or I could tell you something, well, if you measure how the concentration varies with time and you plot it out, it follows a reciprocal relationship, meaning that the reciprocal of the concentration decreases, the reciprocal of the concentration increases with time. There's only one reaction rate, order of reaction that follows that behavior, and that's for a second order reaction. So you can work forward in the sense I tell you the order of the reaction, and then you know what are the appropriate equations, or I tell you something about the reaction in terms of its equations, and you can back out the order. So the best way to do that is with practice. And so I admit I've been negligent. I haven't been posting as many suggested problems as I should. So I will add a list of suggested problems to the Brightspace website out of your textbook for people to work on in preparation for the midterm. Can you go over the relationship between half-lives and reaction rates again? To some extent, I think I kind of did, but I'll give you an example of how they're related. Basically, a half-life tells you something about the rate of a reaction, the fundamental rate of a reaction, meaning its rate constant. We recognize that reaction rates depend on concentration, usually, unless it's a zeroth order reaction. They also have some fundamental speed, which is given by their rate constant. So speaking and thinking in terms of speeds and rate constants is sometimes not how you want to think about it. If I tell you that a drug is eliminated from your body at a rate of 5 milligrams per hour, and you're like, okay, I need to think, I gave this patient 500 milligrams, and then you can back out the calculation of how many hours it could take. Or I could just tell you that the drug has a half-life of 5 hours. And then you know, okay, in 5 hours, the concentration of the drug is dropped to a half. In 10 hours, it's a quarter of that, so on and so forth. So sometimes you want to think about how long a process will take, and that's when you talk about in terms of half-lives. Sometimes you want to know how quickly a process takes, meaning the rate at which it goes, and then you're going to be thinking about in terms of rates and rate constants. And generally speaking, half-lives are inversely proportional to the rate constant. The rate constant goes up, the half-life goes down. And that's true for all of the half-life equations. They all have a slightly different functional form, but let's look to see where they're similar. They're similar in the sense that they're all inversely proportional to the rate constant. And again, that's just coming from the fact that we think of half-life as being a measure of how long a process takes, and that should be inversely proportional to how quickly the process occurs at. And that's given by the rate constant. Why does the half-life not increase as concentration increases for the example you gave? Okay, so I figured there's two. So the question was, why does half-life not increase with concentration? So part of it is because in that question we asserted it had to be a second order reaction. And in second order reactions, the half-life actually decreases as the initial concentration increases. So let me sort of give you two examples. One where a case where the half-life does increase, and one where the half-life does increase, and one where the half-life actually decreases as you increase the concentration. So let me give you like an analogy, and I admit I came up with this analogy a few minutes ago. So this is a Ben Fink original, so it might not be the best analogy. But imagine you're walking down a ladder. So you're walking down a ladder. Or not walking, you're climbing down a ladder. The ladder is 100 meters tall. And you're descending at a rate of 1 meter per second. So the question is, how long does it take for you to get to 50 meters? Well, seems like a pretty obvious question. If you're going at a rate of 1 meter per second, it'll take you 50 seconds. If I can write neatly. 50 seconds. Then you're like, okay, how long does it take me to go from from 50 meters to 25 meters? Meaning I go, okay, first I go down, I start at I start at 100 meters high, I go down to 50 meters high, and then I go down to 25 meters. Well, I'm changing now my height by 25 meters, and I'm going at a rate of 1 meter per second, so that will take 25 seconds. And then how long does it take to get from 25 meters to, say, 12.5 meters? That will take 12.5 seconds. So this is analogous to a zeroth order process. It's zeroth order in the sense that my rate is constant. My rate doesn't depend on how high up I am. So if I were going to plot this out graphically, and I was going to plot my height versus time, I'm descending at a constant rate. So if I start higher, it'll take me it takes me a certain length of time to get to half of that initial height. If I go from there, it will take me, so let me actually plot that out, sketch that out there. To go from half that point, this height down to half of that, that'll take me this much time. To go from this height to half of that height, that'll take me slightly less time. To go from this height to half of that height, it will take me slightly less time. so on and so forth. So it takes less and less time to get to half of where you started from. Again, that's consistent with a zeroth order process. Now consider a different process. I'm going to get rid of these numbers because we're not going to use them. But consider a different process where you're now not descending at a constant rate. Imagine instead of there being nothing at the bottom of this, there's a snake. Something. There's a snake or something that would frighten you. So basically, you know you need to get down, but every step you get closer to it, you become more and more afraid of the snake, and you start slowing down as you descend. So if I were going to plot out my rate of descent, then it would look something like this. I might start here, and as I'm first starting out, okay, I'm really far away from the snake. I don't care. I'm not afraid. As I get closer to it, though, the snake becomes more and more fearful to me, and I start slowing down my rate of descent, basically trying to prolong the inevitable. And that's essentially what's going on with a second order process. As the process proceeds, the rate decreases, and as a result, the half-life lengthens. So at first, okay, when I'm first trying to get down to half of my initial constant, I didn't really draw that very well. Let me try drawing this a little bit better. That's close enough. Time it takes me to drop to half of my initial rate, let me get a different color here. Half the time it takes me to get to half of my initial concentration might be this. To drop down to half of that initial concentration takes longer and longer than it did before. So that's partly because, again, as the process proceeds, as your concentration drops, or in this case, as your height drops, the rate at which you're descending is also slowing down. In that case, your half-life, the time that something takes, should be inversely proportional to your initial height, or in this case, your initial concentration. So again, lower you get, the more frightening the snake, the slower you go. The slower you go, the longer the process takes. Because as we've already tried a logic to ourselves, the half-life should be inversely proportional to the concentration, or inversely proportional to the rate. So again, that's kind of a silly analogy, but conceptually that is how the reaction proceeds. The reaction slows down as the concentration decreases. Okay, so I have a couple questions here. Oh, actually, before I get going, let me answer one more question about this. I like that you went over the answers to the quizzes. It would have been nice if you could have gone over the answers, the true-false questions for the other order. So I only gave the true-false answers if it were a if it were a second order process. So let me actually work through that really quickly right now. So the three observations, or rather the three statements, were: one, if you doubled the concentration of A, that doubled the rate. The second statement was a plot of 1 over the concentration of A is linear. And 3, T1/2 increases as your initial concentration increases. I mean, your half-life gets longer as the initial concentration increases. So again, those are all going to depend on the order of the reaction, whether it's a zeroth, first, or second order reaction. So let me make a little chart here. So whether it's zeroth, first, or second order, and then I'll label each of these as true or false. So if I double the concentration, would that double the rate? That's going to be false for a 0th order reaction. For a 0th order reaction, the rate is constant. It's only equal to the rate constant. For a 1st order reaction, yeah, those are the rate and the concentration are linearly proportional. So doubling the concentration should double the rate. That should be true. For a 2nd order process, that will be false because doubling the concentration, well, the rate goes as the concentration squared. So if you double the concentration, you actually increase the rate by a factor of 4, so you quadruple it. A plot of 1 over A is linear. That's not true for a 0th order reaction. It's only linear if you plot concentration versus time. So that's false. For 1st order reaction, it's only linear if you plot natural log versus time. So that's also false. And then, yeah, for a 2nd order reaction, if you plot the reciprocal of concentration versus time, you get linear line. So that will be true. T 1/2 increases as the initial concentration increases. That will be false for a 1st order reaction. That one is constant. Excuse me, T 1/2, in the case of a 0th order reaction, starting with more material means it will take longer to get through, to react away. Yeah, the half-life there does increase as the concentration increases. And for a 2nd order reaction, the half-life decreases. They are inversely proportional. So those are the answers for the other possible options. So if you said it was a 0th order reaction, the responses should have been false, false, true. For 1st order, it should be true, false, false. And for a 2nd order, you should have had false, true, false. So that's how I will be grading people on that one. On the last part of question 2, okay, so this is a math question, or rather, this is an algebra question. On the last part of question 2, how did you go from 1 over the concentration equals 10.582? How did you go from that to concentration? I'll put it up here. How did you go from this to concentration versus time is equal to 0.0945 molar? Okay, so short answer is algebra. And the algebra is, I know there's a bunch of there's a unit, there are numbers and units here. This represents one thing. I'll call it X. Together, this is just one thing. Yes, there are units ascribed to it, but it's still one quantity, which I'll just call X. And that X should be equal to, its value should be equal to 1 over the concentration. So if I want to solve for concentration, I can invert these. I can cross multiply, whatever. I move this over here, and then I divide by X. So I get 1 over X is equal to concentration at a specific time. So then I plug in 1 over 10.582 inverse molar. Did I have 1 over inverse molar? That second shouldn't be there. If I accidentally wrote second in my solutions, I apologize for that. And I'll make sure the solutions I post will be corrected. So that should be equal to the concentration, and then 1 over 10.582 is equal to 0.0945. So there's that. Okay, so this is a question about the potential energy curve. How do you tell when the potential energy curve is higher than at the start of the reaction than at the end? So basically, how do you tell when you have a potential energy curve? How do you tell if this ends up lower or if it ends up Short answer is it depends on whether the process is exothermic or endothermic. This is a process where you have a net drop in energy, so these are both representing energy here, and to be more specific, they represent potential energy. So this is reaction, both of these are reaction progress. In this process, as I go from reactants to products, I have a net drop in energy. So for this one, the change in energy is negative. This is an exothermic process. And this one is an endothermic process because the energy change is positive. So how do you know whether it goes up or down basically is asking how do you know whether a reaction is exothermic or endothermic. And there may be some indication of that. If the reaction is described, I tell you the reaction system heats up, that means that it's releasing thermal energy, meaning it's exothermic. So then you could predict that that's what it looks like. There will be some indication to tell you whether it's exo or endothermic. Later on, when we talk about thermodynamics, we are going to spend a little bit more time on thermodynamics and the chemical aspects of it. You can look at the relative energies of reactants versus products. You can we won't have absolute energies, but we'll come close to having something that's like an absolute energy. The energy of this minus the energy of that could tell you, okay, is methane and 2 oxygen molecules, is that higher in energy or lower in energy than a carbon dioxide molecule and 2 water molecules? It's not immediately obvious. There are ways to calculate which of these is more energetically favorable, whether this is energetically favorable or that's energetically favorable. If this is energetically favorable means a drop in energy. So this does happen to be more energetically favorable, partly because of the carbon-oxygen bonds are a little bit more stable than the carbon-hydrogen bonds. And also those hydrogen-oxygen bonds are pretty stable. So the point being that this one ends up being lower in energy, so it's a drop down in energy, so it's exothermic. So again, that is hard to predict. Even when you are familiar with doing that analysis, it's not trivial. So we haven't even gotten started into how to do that analysis. I think the other sections have done a little bit more work with Hess's law. I didn't spend much time on that last semester in my section, so I am going to work through Hess's law and working with absolute enthalpies and enthalpy changes. I'm going to be working through that again in my section this semester, so we'll have that to work on. The point being is, how do you predict it? At this point, it's not easy to predict it. You need to know ahead of time whether it's an exothermic or an endothermic process. The Arrhenius equation is still a little confusing to me. Why do you use it, and what do you solve for with it? So the Arrhenius equation I spent some time in the lecture talking about this first term, the pre-exponential factor, trying to explain what it is. And essentially, it does represent the rate of, I'll say it's the number of properly oriented collisions per second. That's just what it is. What do we care about that? Usually we really don't. The parts of this equation that I want you all to focus on, that I think are important, are the activation energy and the temperature, and how they relate to the rate constant. That is what you get conceptually out of the Arrhenius equation, is how does a reaction rate depend on temperature, and how does it depend upon the energetics of a reaction? How much energy do you need to put in to get the reaction to go forward? That's given by the activation energy. So in terms of what you would be solving for with it and what you'd be thinking about with it, usually I will be asking questions that in some way relate, how does the rate of a reaction, how does the rate constant for a reaction depend on energy and time? We've been mostly working with rate laws, and I have to admit, I don't think I've ever seen anybody write something out like this, but I will write it out for people. Let's say I have a first order reaction. Then I can tell you the rate of that reaction is equal to A e to the minus activation energy over R times T times, you know what, that's a bad example that I'm going to use here. Let's, ooh, goodness. Oh, that's annoying. I'll say just concentration of B, of some you know, even better, concentration of R, concentration of some reactant. So previously we've just seen things like this, rate is equal to K times R, because usually when we first start talking about reactions, we're just concerned with, okay, how the rate law tells you, how does the rate depend on various factors? One thing it depends on is the concentration. The other thing it depends on is the temperature. Higher temperatures have increases the rate of a reaction. So if I include the Arrhenius equation in my rate law, I'll have that explicit temperature dependence in my rate law. The Arrhenius equation, again, just generally tells you how does the rate depend upon the energetics of a reaction and the temperature at which that reaction is being utilized. So you can look in the proposed homework questions. I already admitted I'm going to lop off some of those because we didn't have a chance to cover them before I was going to make the homework assignment due. But you can do calculations where, okay, given the rate constant and at certain temperatures, you can calculate the activation energy. One way you can do that is graphically. So there's another question is, how did you graphically get the slope? So I'll run through that again here, which is that if you take the natural log of this equation, so I have natural log of K is equal to natural log of A e to the minus negative EA over RT. It is a property of logs. There's two properties of logs here I'm going to apply. One is that if you have natural log of two terms, A and B, that's the same thing as natural log of A plus the natural log of B. So I'll apply that here. So I have natural log of K is equal to natural log of A plus natural log of e to the minus EA over RT. And then I will tell you another relationship regarding logs, which is if you have natural log of E, what is E? If you have a natural log of E to some number, that's equal to that number. So it's a way, gives you, the reason why I'm taking the natural log is I'm trying to get rid of that exponential term and trying to make it somehow linear with respect to temperature and not go as the exponential of temperature. So out of this will come natural log of K, natural log of A, minus EA over R times temperature. So I'm going to take out that negative exponential term and I can bring it down here out of the logarithm, out of the exponential. Why is this equation useful? Well, if you measure the rate constant at various temperatures and you plot out natural log of K versus 1 over temperature, you will get a straight line. So if I plot natural log of K versus 1 over the temperature, I get a straight line. Why do I get a straight line? Let me break this down a little bit here. So I should have, yet again, So I have natural log of K is equal to natural log of A minus activation energy over R times 1 over temperature. And I'm going to break this down a little bit more. Here's one term, here's another term, and then here's another term. So if I try to make this look like a linear equation, it's linear if I say, okay, x is 1 over t, m is, my slope is negative EA over R, and then my y-intercept is the natural log of A. And if I say my dependent variable y is the natural log of K, okay, this will then have a linear slope if I plot natural log of K versus 1 over the temperature. And in that case, the slope of this line is equal to negative activation energy over R, the gas constant. So that was another question somebody had. What is R? R is the gas constant. And yeah, it is the gas constant from the ideal gas law. And that can be surprising to some people. It's like, we're not talking about gases, are we? We're talking about reaction rates. That's because even though it's called the gas constant, it applies to more than just gases, meaning it's the gas constant is actually is like a fundamental constant, in the same way that c, if you all remember from when we were doing quantum, c was like the fundamental speed of light, h was Planck's constant, it's just some fundamental constant of the universe. The gas constant is another fundamental constant of the universe, and it relates to how energy is distributed at different temperatures. So that's true. That comes into play when you talk about the ideal gas law, and it comes into play here when we talk about the average energies that a system has at various temperatures. So if we think about, okay, the idea being the reaction has an energy barrier that you need to get over. Only a certain fraction of your particles are going to have enough energy to get over that. The fraction of them that have that increases at higher temperatures. And the way that scales, the way the fraction increases, is related to this fundamental constant, which is the gas constant. So somebody else was asking what units or what value should you use for the gas constant. I will recommend you use 8.314 joules per mole Kelvin. The other form that you may be more familiar with, which is 216, I think, liters atmosphere per mole Kelvin. That number is value. These two values are equivalent. They only differ in terms of a unit conversion. And you can use this value, but then your activation energies are given in units of liter atmospheres, which is not a standard unit of energy. It has dimensions of energy in the same way that, like, cubic centimeters has units of volume, and 1 cubic centimeter is equal to 1 milliliter. I don't know off the top of my head. I think I should take that back. Again, it's 101.325 joules is equal to 1 liter atmosphere. So we will frequently want to express our units in units of energy units, in units of joules. Those are just the more common units to use. So in that case, I will recommend people using 8.314 joules per mole Kelvin. Why does a graph give you activation energy? Okay, I think that's all the points I wanted to get across here. All right, so if you have any further questions, please shoot me an email or drop by my office either later today or on Monday and Tuesday. Otherwise, I will see you all on Monday. Have a good weekend, everyone.